Look up at the night sky. What do you see? A dazzling array of stars, each a distant sun. Our universe is teeming with these celestial objects, each with a story to tell. Just like us, stars have a life cycle. They are born, they shine, they age, and ultimately, they die. But the way a star lives and dies is far more dramatic than anything we experience here on Earth. Stars are not just pretty points of light, they are the engines of cosmic evolution. They forge the elements that make up everything we know, from the carbon in our bodies to the iron in our blood. Understanding the life cycle of stars is to understand the universe itself, its origins, its evolution, and ultimately, our own place within it. Join me on this cosmic journey as we explore the fascinating life and death of stars. From their birth in interstellar clouds to their dramatic demise, we'll uncover the secrets of these celestial giants. We'll delve into the heart of stars, where nuclear fusion unleashes unimaginable energy, and witness the awe-inspiring power of supernovae, the most powerful explosions in the cosmos. So fasten your seatbelts, space cadets, and get ready for a journey through the cosmos. A journey that will illuminate the fascinating life cycle of stars and reveal the wonders of our incredible universe. Stars are born in vast cold clouds of gas and dust scattered throughout galaxies. These clouds, called nebulae, are like cosmic nurseries, cradling the ingredients needed to create a star. Imagine a cloud so large it could hold millions of suns. That's the scale of a nebula. Gravity is the driving force behind star formation. As a nebula drifts through space, random fluctuations can cause denser regions to form within it. These regions, pulled together by their own gravity, begin to collapse in on themselves. As the cloud collapses, it heats up, spinning faster and faster. Think of a figure skater pulling their arms in during a spin. They spin faster and faster. The same principle applies to our collapsing cloud of gas and dust. This spinning, collapsing cloud is called a protostar. As the protostar continues to collapse, the temperature and pressure at its core increase dramatically. Eventually, the core becomes so hot and dense that nuclear fusion, the process that powers stars, ignites. A star is born. Nuclear fusion is the heart and soul of a star, the engine that makes it shine. Imagine the power of 1,000,000 hydrogen bombs exploding every second. That's the energy output of a typical star. This energy is generated deep within the star's core, where temperatures reach millions of degrees and pressures are unimaginable. Fusion is the process of combining lighter elements into heavier ones, releasing tremendous energy in the process. In the core of a star, hydrogen atoms, the simplest and most abundant element in the universe, are fused together to form helium. This fusion reaction is what powers the sun and all other stars. Think of it like this. Imagine 4 cotton balls representing hydrogen atoms. When squeezed together with enough force, they fuse to form a single marble, representing a helium atom. The squeezing represents the intense pressure and heat within the star's core. But here's the catch. The marble is slightly lighter than the 4 cotton balls combined. This tiny difference in mass is converted into a tremendous amount of energy. According to Einstein's famous equation, E equals mc squared. This energy, in the form of light and heat, radiates outward from the star's core, pushing against the inward pull of gravity. This delicate balance between the outward pressure of fusion and the inward pull of gravity is what keeps a star stable and shining for millions or even billions of years. Once a star achieves a stable balance between gravity and nuclear fusion, it enters what astronomers call the main sequence. This is the longest stage in a star's life, akin to our adult years. Our Sun, a typical main sequence star, has been shining for about 4.6 billion years, and will continue to do so for another 5 billion years or so. During the main sequence, a star fuses hydrogen into helium in its core, steadily releasing energy. The color and brightness of a main sequence star depend on its mass. Massive stars are hotter and brighter, appearing blue or white, while less massive stars are cooler and dimmer, appearing yellow or red. Think of it like a bonfire. A large bonfire burns hotter and brighter than a small campfire. Similarly, massive stars burn through their hydrogen fuel much faster than their smaller counterparts, leading to shorter but more spectacular lives. Our Sun, a relatively small star, is somewhere in the middle, shining with a yellow light. Its moderate mass allows it to live for billions of years, providing a stable source of energy for life on Earth to flourish. Section 5. Red giants, stars in their twilight years. As a star ages, it gradually runs out of hydrogen fuel in its core. With no more fusion to counteract the relentless pull of gravity, the core begins to contract and heat up. This heating causes the star's outer layers to expand outward like a balloon being inflated. The star swells up to an enormous size, becoming what's known as a red giant. Imagine a campfire as the wood burns down, the embers glow red hot. Similarly, as a star begins to exhaust its fuel, it cools down and glows red, hence the name red giant. During this red giant phase, the star's core becomes a furnace, hot enough to fuse helium into heavier elements like carbon and oxygen. This process releases even more energy, causing the star to become incredibly luminous, though cooler than it was during its main sequence years. Our Sun, in about 5 billion years, will swell up into a red giant, engulfing the orbits of Mercury and Venus, and possibly even Earth. Don't worry though, we have plenty of time to figure out our next cosmic address. Section 6. The spectacular demise of massive stars, supernovae. While our Sun will end its life relatively peacefully as a white dwarf, massive stars meet a far more dramatic fate. These stellar giants, several times heavier than our Sun, live fast and die young, ending their lives in spectacular explosions called supernovae. As a massive star runs out of fuel, its core collapses under its own immense gravity. This collapse happens so rapidly and violently that it generates a shockwave that tears the star apart. This explosion, a supernova, is one of the most powerful events in the universe, briefly outshining an entire galaxy. Imagine a firecracker exploding in slow motion. That's a crude analogy for a supernova, albeit on a much grander scale. The energy released in a supernova is so immense that it can briefly outshine all the stars in its host galaxy. Supernovae are essential for cosmic evolution. The intense heat and pressure during the explosion forge heavy elements like gold, silver, and uranium, elements heavier than iron that cannot be created in the cores of ordinary stars. These elements are scattered throughout space, enriching the interstellar medium and providing the building blocks for future generations of stars and planets. Section 7. Stellar remnants, white dwarfs, neutron stars, and black holes. After a star exhausts its nuclear fuel and dies, it leaves behind a stellar remnant, the corpse of a once mighty sun. The type of remnant depends on the star's initial mass. Small to medium-sized stars like our Sun end their lives as white dwarfs. A white dwarf is the hot, dense core of a star that has shed its outer layers. It's about the size of Earth, but incredibly dense, with a teaspoonful of white dwarf material weighing as much as an elephant. Imagine squeezing the Earth down to the size of a basketball. That's the density of a white dwarf. These stellar embers slowly cool down over billions of years, eventually fading away into darkness as black dwarfs. Neutron stars are the remnants of massive stars that have gone supernova. They are incredibly dense, even denser than white dwarfs. Imagine squeezing a star as massive as the Sun into a sphere the size of a city. That's the density of a neutron star. A teaspoonful of neutron star material would weigh billions of tons, about the same as Mount Everest. Black holes are the most extreme stellar remnants, formed when the core of a massive star collapses to a point of infinite density. Their gravity is so strong that nothing, not even light, can escape their grasp. Imagine a cosmic drain, pulling everything around it into its abyss. Section 8. The circle of stellar life. The life and death of stars are not isolated events. They are part of a grand cosmic cycle. The material ejected into space during a star's lifetime, through stellar winds or supernova explosions, enriches the interstellar medium, the space between stars. This enriched material containing heavy elements forged in the hearts of stars becomes the building blocks for future generations of stars and planetary systems. Think of it like a cosmic recycling program. Stars are born from the ashes of their predecessors, enriching the cosmos with heavy elements and seeding the universe with the ingredients for life. Our own solar system, including Earth and everything on it, is made from the remnants of long-dead stars. The atoms in your body, the calcium in your bones, the iron in your blood, were all created in the cores of stars billions of years ago. We are, quite literally, stardust. Section 9. Our place in the cosmic dance. As we gaze up at the stars, we are witnessing the grand cycle of stellar evolution unfolding across vast stretches of space and time. Stars are born, they shine, they create the elements that make up our universe, and ultimately they die, sometimes in spectacular fashion, seeding the cosmos with the ingredients for new generations of stars and planets. Our own sun is a relatively unremarkable star, but its existence is essential for life on Earth. Its steady light and warmth have nurtured life on our planet for billions of years, and its eventual demise will mark a dramatic turning point in Earth's history. Understanding the life cycle of stars allows us to appreciate the interconnectedness of the universe. We are not just passive observers in this cosmic dance, we are active participants, our very existence intertwined with the birth, life, and death of stars. So the next time you look up at the night sky, remember that you are looking at a snapshot of cosmic evolution in action. Each star has a story to tell, a story of creation, destruction, and rebirth, a story that ultimately connects us all.